So in this video, we are continuing our review of probability, starting with conditional probability, which is defined as the probability that A occurs given that B has occurred. And it's written as probability A with a vertical line B. The formula for it is the probability of the intersection of A and B divided by the probability of just B. And so to represent this visually, we'll use a Venn diagram. Not necessary to use a Venn diagram in these questions, but it's an easy way of understanding it. But here, the total probability adds up to 1. And the probability of just the B circle is the 0.1 region plus the 0.3 region. So the probability of B here is 0.4. And the question would be, what is the probability of getting something in A given that you've pulled out something in B? So it sort of restricts your denominator to just the B circle. So if you think about just reaching into the B circle and pulling something out, what is the probability that the thing you've pulled out is also in A? And so here that ends up being the 0.1 overlap region and divided by the 0.4 that you pulled from, and you get a 1 in 4 chance that if you pull something out of B, that element is also in A. Transform that formula, you get the multiplication rule. So it's the exact same formula, just with the probability of B moved to the other side of the equation. So you just need to be familiar with this format because this is how it's going to appear in the formula booklet that still has conditional probability in it. Here's a simple example that sort of goes on the concept of conditional probability, but you won't need a Venn diagram or the formula to do it. It's pretty simple. We have 6 green toys and 4 red toys placed in a container, and a child is asked to select 2 toys at random. So this you can think of as an event followed by another event. Even if the kid selects 2 toys at the same time, the selection of one actually does change the probabilities for the selection of the other. So you can think about this as one event followed by another event where you've changed the probabilities after you've pulled out one of the toys. So it lends itself to a tree diagram where the first options are either 4 out of 10 to pull out a red, 6 out of 10 to pull out a green. But then once you've selected a toy, now there are only 9 in the container. And so the next set of branches, if you've already pulled a red, then you're only going to have 3 red remaining out of 9 total, while there are still 6 green out of 9 total. If you've already pulled a green, then there are still 4 red remaining out of the 9 total, but there would only be 5 remaining of the green out of the 9 total. And so this is the overall tree diagram for this problem. And then we just have to see what it's asking us. What is the probability that the child would choose 2 red toys? And here we have to remember that to go down a tree diagram, you multiply along the branches. So 4/10 for the first red times 3/9 for the second red. And that's going to be 12 over 90, which reduces to 2 over 15. So worth renoting in case you've forgotten that for tree diagrams, you multiply to get to the end of each branch, and then you would add different branches together if necessary, if more than one branch satisfied the conditions that are being asked about. So for example, 6 peppermints and 2 licorice, a candy is picked and not replaced in the bag, and then a second candy is picked. So another tree diagram where the probabilities have changed along the second set of branches. So to create this tree diagram, you'll have to go down the several pathways of, so if a peppermint's already been selected, then now there's only 5 left, and overall there would only be 7 candies remaining, and so on. So you create this probability tree, and then look to the questions being asked. So part A, find the probability that one of each type is chosen. So you can think about that as these 2 branches, right? P followed by L, or L followed by P. And multiply along to get to the end of each branch, get 12 out of 56 for each of those paths, and then add the 2 12 out of 56s together to get a 24 over 56 chance, or 3/7 chance, that one of each type would be chosen. Part B is a conditional probability question. Given that one of each type was chosen, find the probability that the first one was a peppermint. So now this is restricting the paths that we're selecting from. Normally this question would have 4 possible paths, PP, PL, LP, or LL. But when it says given that one of each type was chosen, that means we're only considering the 2 paths PL or LP. And it's saying, out of those 2, what's the probability that the first one chosen was a peppermint? So we could set up this probability problem, the probability of a peppermint followed by licorice divided by PL or LP, the combined probabilities. And so this ends up being 1/2. So there's a 50-50 chance that if you've got two candies in your hand, one of each type at the end, that the first one drawn was a peppermint. In an experiment to study color blindness, we have some data. So statistics being pulled from data can be a slightly different approach. It's actually a little easier, I think. So for example, what's the probability that a person is colorblind in this story, given that the person is a woman? So the way I tend to think about this is I look to the condition first, so given that the person is a woman. And I say, so that means rather than selecting out of the 1,000 people in this overall data set, I'm actually only selecting from the women. And so the females here are 490 total. And then I'm looking just to those to determine what my numerator would be. So just out of the females, where are the colorblind set? And that's just 2 people. So when I go through that process, I'm imagining first what the denominator is going to be. Then I'm looking to just that denominator set to pull out what the numerator should be, and then reducing it. So the probability ends up being 1/245. Now we haven't used the formula for conditional probability, but we could here. I'm just going to show you why you would end up really not needing it, because the formula would say actually to figure out this, the probability of the intersection of these two things, colorblindness and being a woman. So the probability of the intersection of these two things, meaning if I reached into this set of 1,000 people, what is the chance or the probability that I'm going to pull out somebody who is both colorblind and a female? And so that's going to be a 2 out of 1,000 probability for just the numerator. And then the denominator is supposed to be the probability of just the condition itself, which is the probability of getting a woman. So from this set, if I pull in, reach in and pull somebody out, I'm going to get a 490 out of 1,000 chance that I get a woman. So then you could set up 2 over 1,000 over 490 over 1,000. And then notice that the thousands would cancel out and you'd be left with 2 over 490, which is the same exact answer that we had above. So you don't need to express it as probabilities to begin with, because the denominators will be the same if you're doing it based on a statistical set like this. Here we just have some pure probabilities given. So rather than any numbers or data, they just give us probabilities. Probability of D is 0.83. Probability of A is 0.92. And the probability of A and D, so the intersection, is 0.78. And then this asks us to find 2 different conditional probabilities, A given D and D given A. So the purpose of this question is to illustrate that actually those will be 2 different calculations. So A given D is going to be the intersection divided by the probability of D. But D given A is going to be the same intersection divided by the probability of A. So you just have to pay attention to the order of the conditional probability, either in the parentheses or in the question, to make sure that you're putting the correct probability in the denominator. And then finally, another data sort of data-driven question, but it's with percents or probabilities rather than with raw numbers. So what we're told is that 81% of drivers stopped are given a breath test and 40% are given a blood test. And it says 25 are given both. So that's enough information really to draw the Venn diagram of this with a little backwards thinking. I might do that because I see the questions that are following, and it might be helpful if I had all the probabilities spelled out in a Venn diagram. So in this Venn diagram, what I know is that, and I've expressed them as probabilities, so the sum total is 1. What I know is that 25% get both tests. So the overlap has to be the 0.25. I start from the center when I fill these out. And then if 81% stopped or given a breath test, that includes the 25 who get both. So I subtract 25 from 81 to figure out that 56% are in the breath test circle, but not the overlap region. Do a similar process for the blood test, 40 minus 25%, and fill in each of those distinct regions. And then add those up, you'll see that the only amount left over is the 0.04. That's what I put outside of both tests. And so that shows me that there's a very small probability that somebody who is stopped is not going to get either test. And now I can answer the questions pretty easily. Probability that a suspected driver is given a test. So that's any test. It's going to be the 96% figure. Probability that they're given exactly 1. That's going to be the 56% that get just the breath test, or the 15% that get just the blood test. And that sum is 71%. Probability of no test, that's the 4% that's on the outs. And then are giving the two tests independent? And this is not a common sense question. This is a mathematical proof where you're checking to see, we haven't done one of these, but it was in a previous video. To test for independence, you have to see if it fits this equation, if this is true for the given set of information. And so I've got the intersection region as 0.25. I have the two independent or separate probabilities of A and B. But when I multiply these probabilities of A and B, I do not get the probability of the intersection region. So when those are not equal, we can conclude that these are not independent events. That is all.